In this problem, I'm going to be looking at the electric potential due to a uniform disk of charge. And the first thing I have to do is, I've made a sketch of this disk, and the strategy is going to be take an individual ring that is one part of the larger disk and analyze the contribution at some point along the z-axis. Let's call that point P. The contribution of the electric potential at point P due to that individual ring. And so I'm going to need to make a couple of statements. I'm going to need to talk about surface charge density. We'll use the Greek character sigma to describe surface charge density, and we'll say that surface charge density is the total charge over the total area of the disk. Additionally, we can say that the area of the disk is pi capital R squared. I suppose now would be a good time to take a look back at the individual sketch and recognize that capital R is going to be the radius of the larger disk, and lowercase r, which we'll call little r right there, is the distance to one of the particular rings that make up the larger disk that we're inspecting. So if I go back up here to these kind of additional statements, we're going to look at the individual surface charge density of one of the rings. Let's call that dq, or the differential of q, the tiny amount of charge on that particular ring. And we'll describe it as the circumference of the ring, so it's going to be 2 pi little r, times the thickness of the ring, which we'll call dr, or the differential of r. That allows me to say then that I can kind of develop this expression for just dq. dq is going to be equal to sigma, the surface charge density, times 2 pi little r dr. So really what I'm doing here is multiplying this in the denominator on both sides. When I go back to the larger expression, I can say that Q, the total charge of the larger disk over pi r squared, is equal to sigma. So really what I'm going to do is substitute in for sigma right here, Q over pi r squared. And so that leaves me then at this final expression for dq, which is just going to be equal to Q over pi capital R squared. Now I have to kind of add all this stuff, make sure that it's still in there, times 2 pi r dr. Now for starters, the pi cancels out, and so I'm left with Q times 2 times r dr over r squared. Additionally, another kind of initial condition is I have to answer the question, how far away is point P from the ring? And so this line extends back to point P. Let's call that r sub I. And the distance that point P is along the z-axis we'll call z. And this is three-dimensional, so it's a bit tough to see. Little r is in another side of this right triangle. And so I can just establish using Pythagorean Theorem a squared plus b squared is equal to c squared, where the c side, or the hypotenuse, is ri squared. And the other sides are r squared and z squared. So now I can develop this expression for ri. It's going to be equal to the square root of r squared plus z squared. Okay, now that my initial conditions have been established, I'm going to say that the differential of voltage at point P, the tiny contribution of voltage from the ring, is going to be equal to kq over r, or in other words, 1 over 4 pi epsilon naught, that's our constant k, times the differential of charge dq, the charge contribution of that tiny ring of the larger disk, over r sub I. This is effectively the electric potential due to a point charge, but we're treating this tiny ring here. All right, so the next thing that I'm going to do is I'm going to take the integral of both sides. I'm going to say that the integral of all those little differentials of potential is equal to 1 over 4 pi epsilon naught, which is a constant, times the integral. This is going to be the integral between r equals 0 and r equals capital R. In other words, we're going to start with a tiny little ring right here at the origin, and the radius of that ring gets bigger all the way until it reaches the extents of the disk. I need to make my substitution in for dq, which I will do. This becomes 2 times q. I've just rearranged that. And I get r dr, and in the denominator, I get capital R squared, but I can't forget the ri that was in there originally. So that kind of second step is going to involve this substitution in for dq right here. Let's just go ahead and make that clear. And then the last substitution that I'll make in the next step is going to be to substitute our expression for ri right here into the denominator here of my expression. But before I do that, let's acknowledge that the integral of the differential of the voltage, if I just add up all those little pieces together, it's just going to be the voltage at point P. I do want to pull out some constants here in the numerator. 2 is a constant, and so is Q. And it's going to be over 4 pi epsilon naught. I also want to pull out capital R squared out of the denominator here. That's a constant. And I'm going to be taking the integral between r equals 0 and capital R. And then I'm left with, in the numerator, r dr, and in the denominator, I'm left with the square root of r squared plus z squared. So I'm in good shape here. I'm going to make a quick, reduction here. The 2 and the 4 reduced to a 2 in the denominator. And, I'm going to just rewrite this to make it a little bit more clear. This is Q over 2 pi epsilon naught r squared times the integral of from r equals 0 to r equals r of r squared plus z squared. And I'm going to put this in parentheses and raise it to the negative 1/2 because that's the same thing here, times r dr. Now here's where it gets a little interesting. I'm going to have to use some new substitution rules. If I take a look at this and define u as r squared plus z squared, then I can say that du is going to be equal to simply 2r. So I want this to take the form of u du, so I need to put a 2 in front of the r, which means that if that's all I did, I would change the value of this voltage that I'm looking for, this electric potential. So what I'm going to do is I'm going to take into account, or I'm going to account for that by putting a 1/2 in here. So really, I'm not changing the value of the expression. I've put in a 1/2 here and a 2. That's 1. So that allows me to move forward now, and that leaves me with the electric potential at point P is equal to Q over 4 pi epsilon naught r squared. And now I'm going to be taking r squared plus z squared to the positive 1/2. And I have to remember that there's a 2 in front of it. So it's 2 times r squared plus z squared to the positive 1/2. And that's going to be evaluated between 0 and capital R. So let me bracket this piece off so I'm not mixing it up with what I've done before. Let's keep it separate. So now I'm ready to proceed. And I'm going to finish my work over here. So my next step is going to be up here. The next thing that I'm going to do is I'm going to say that the potential at point P is equal to Q over 4 pi epsilon naught r squared times, now I'm going to factor out this 2. So when I factor out the 2, it's going to go there. Actually, you know what? Let me factor out the 2 in the next step so it's a little bit more clear what I did. This becomes 2 times z squared plus r squared to the 1/2 minus 2 times z squared plus 0 squared to the 1/2. Now that's just z squared to the 1/2, or z. Now I can factor the 2 out. I think you can kind of see what's going on here. I've got 2 as a coefficient in front of each one of these 2 terms in the binomial. When I factor out the 2, I get a 2 in the numerator, 2 times q. We can see what that's going to do with the number 4 in the denominator, 4 pi epsilon naught capital R squared. And I get z squared plus capital R squared to the 1/2 minus z. The 2 and the 4 reduce, and I'm done. I'll just kind of rewrite this one last time. The electric potential is equal to Q over 2 pi epsilon naught capital R squared, that's the radius of the disk, times z squared plus r squared minus z. And so now I have an expression for the electric potential at some point a distance away from a uniformly charged disk.